Hello, everybody. Let's start the lecture. I recall that a week ago we studied the following Markov chain X of n on integer numbers with transition probabilities 1/2 from every non-zero I to its neighbor, and transition probability from 0 to 1 was p, and transition probability from 0 to 1 to -1 Skew, that is equal 1 minus p. So these xn have transition probabilities like simple symmetric random walk everywhere, but when it hits 0, it has a perturbation and it goes up with probability p and it goes down with probability q. In particular, if p is 1/2, then we have simple symmetric random walk, and if p is 1, then we have reflected random walk. And we calculated transition probabilities for xn, and we formulated the following theorem, that x and t over square root of n, this process converges in distribution to the so-called Skew Brownian motion with parameter gamma that is equal to p minus q or 2p minus 1. And a Skew Brownian motion is a Markov process with transition probability density functions ptxy that is equal to phi t y minus x plus gamma times sine of y times phi t absolute value of x plus absolute value of y, where phi t is a Gaussian density, is 1 over with 0 mean and variance t. And here t is positive and x, y are real numbers. We see that if p is 1/2, so p is q is 1/2, then gamma is 0, and we have just transition probability density of a Brownian motion. Well, we proved convergence of one-dimensional distributions. Actually, we haven't proved convergence in distribution because we need some theory on this topic, like tightness of distribution or weak relative compactness, and the standard arguments are prove weak relative compactness and convergence of finite dimensional distributions. For people who know weak relative compactness, we have to estimate modulus of continuity of these processes, and it's not so hard if you know estimates for modulus of continuity of simple symmetric random walk. A little bit later, we will see construction of this xn as a certain function of simple symmetric random walk, and something else. Today I will discuss properties of this object, skew Brownian motion, different ways of construction of skew Brownian motions. Also, I will present stochastic differential equations for skew Brownian motion. Some results will be formulated without proof. Okay. The first topic is Ita and McKean definition of a skew Brownian motion that they gave in their book Diffusion Processes and their Trajectories. So actually they gave the name for certain process, and it was an exercise to study its properties. At first, let's discuss again xn. And the way how we can obtain xn as a certain function of simple symmetric random walk. Okay, assume that we have simple symmetric random walk. So we go up and down with probabilities 1/2. The path between two zeros, so this path, this, well, this I will call excursion. Oops, not this. So it starts here. Okay, it's called excursions. Well, if the random walk doesn't start at 0, I will not consider this part of the trajectory. So this is excursion number 0, and we do not touch it. Now let us make the following procedure. We enumerate this excursion in any measurable way. Okay, for example, we may say this is first excursion, second, third, fourth, and so on. However, we can say this is first, this is second, this is third, this is fourth, and so on. So it's not really a problem. And then toss a coin and make the following procedure. So we put excursion above 0 with probability p and place excursion down with probability, for example, p, we say success if probability is p, and failure if probability is q. So pluses will be successes, minuses will be failures, and we will obtain the following picture. So this excursion, we flip it. So we place it up. And then this plus, we leave it as it is. So minus, we leave this excursion below. Okay, minus, we make a picture of this excursion, but with sign minus, and so on and so forth. Actually, it's more or less clear that if you make this procedure, then the distribution of the Markov chain that we obtain is xn. Indeed, if the random walk is not at 0, then original random walk, then it jumps up and down with probability 1/2. What are we doing here? We at first, okay, you may say the following. You consider just absolute value of every path and then multiply by +1 with probability p and with -1 with probability q. And if you have different excursions, well, these choices like +1 and or -1 should be independent. I forgot to say this, to mention this. They should be independent of the random walk, and these turns. So everything is independent. Well, and we don't touch the excursion number 0 if it exists. If you start from 0, you may flip it also. Yeah, so you see that outside of 0, probabilities are 1/2 and they're independent of the past. And if you're at 0, then it is a start of a new excursion, and you select a sign of excursion independently of the past. Okay, and Ito McKean proposed to do the following thing. Consider a Brownian motion. Or reflected Brownian motion. So it has excursions. However, you have to be very careful because when it is well known that if Brownian motion hits 0, then in any neighborhood of this point, there are infinite number of excursions. So it's like this, and here there is a small excursion, and here. So to say the truth, there is no next excursion. So when one excursion ends, there is no another one. Between any two excursions, there is infinite number of very, very small excursions. And excursion is a path between two zeros. Then you enumerate excursions, except of this problem, in any measurable way, and then multiply excursion by 1 with probability p, and negative with probability 1, and these random variables, so signs +1 or -1, are independent and are independent of this reflected Brownian motion. So sometimes you flip the excursion, for example, this. I don't discuss the first one. And some excursion you leave as they are. So Itten and McKean called this process a Skew Brownian motion. A Skew Brownian motion. Well, and this is more or less clear that no, it's natural to expect that Donsker scaling limit of this random walk is a Skew Brownian motion, because you see, we may start from Brownian motion or from reflected Brownian motion and then select signs. And here we do the same. And we know that reflected random walk converge to reflected Brownian motion. So probably when we select signs of excursions, you have the same limit. Well, it's possible to prove. However, you have to be very careful with the details of the proof. Another delicate space is the following. I say we have to enumerate all excursions in any measurable way. And here, the way how we enumerate excursion Okay, we can say take first, second, third, but now there is no first, second, third, and so on and so forth. So you have to invent some algorithm. Okay, so the algorithm may be as follows. At first, notice that with probability 1, the first fact, there is at most countable, okay, there is a countable number of excursions. There is countable number of excursions with probability 1. The question for you, why this is true? Any ideas, Gennady? Vadim?
Well, seems that the set of maxima is no more than countable.
Could you please repeat? I didn't hear.
The set of local maxima is no more than countable.
Yes, this is true. And what is the relation between local maximum and excursion?
So if we have excursion, then we have at least
Yes, actually, this is true that the number of excursions is less than or equal to the set of local maximum. Well, yeah, but the simpler proof is the following. There is at least one rational number at this set at the interval, like left end of excursion, right end of excursion. So uh, amount of excursion so is at most countable. And then we can do, okay, second, enumerate. And the algorithm may be the following. At first, we enumerate all, no, enumerate. The second question is, every end of excursion, so left end of the excursion interval and right end point of the interval are not rational numbers. So ends of excursions intervals are not rational numbers, again with probability 1. Well, and why do we have this? Because Brownian motion or reflected Brownian motion, which can be constructed as absolute value of Brownian motion, has continuous, so its one-dimensional distributions are continuous. So for every rational time, a probability that Brownian motion or reflected Brownian motion is at 0 is equal to 0. And if for every rational number the probability is 0, then probabilities that there exists rational t such that Brownian motion is at 0 does not exist countable sum of zeros, which is 0. And the third, enumeration. We enumerate rational number in any So arbitrary, so T1, T2, T3, and so on. And then we may do as follows. Take the number T1. Well, we know that with probability 1, excursion of reflected Brownian motion, reflected Brownian motion is positive here. Then actually you may understand, you may find the right point. So it is infimum of S such that the reflected Brownian motion is at 0. So verify that the right end and then the left end of excursion are random variables, so are measurable. Well, it may happen that T1 is here, and when you go left, then there is no zeros here. Okay, you can distinguish this case also. Well, if T1 is here, just skip this step. If T1 is here, then this is excursion number 1. Then you go to T2. There are 2 possibilities. T2 is here. 3 possibilities. T2 is here. Then skip this set. T2 is at this interval. Again, skip. Or T2 at another excursion. Then if T2 is here, then you say this is excursion number 2. Then you take T3. If T3 is here, here, or there, then skip the set. If it's somewhere else, then you say that this is excursion number 3. For example, T1 is here, T2 is here, T3 is here. Okay, this is not excursion. Then you take T4, assumes it appears this, then this excursion number 3. And actually, this is a measurable way to distinguish, for example, left end of excursion, right end of excursion, to enumerate excursion, and then you multiply all this path by eta 1, eta 2, eta 3 that are IID and have values plus and minus 1 with probability P and Q respectively. So this is construction of eta and McKean. Eta and McKean. Well, it is not clear from the very beginning that this is a Markov process, and the transition probability density functions of this Markov process are like this. So this can be done, and this is really interesting exercise to solve. And now a few words about modulus of continuity and weak relative compactness of for this. And I would like just to mention the way of investigation and the way of investigation and just advices. So assume that we start from reflected Brownian motion, and then we construct this X. And assume that you have 2 points K and L, and let's estimate maximum over all I and j between k and L of xi minus xj. So you take 2 points, I and j, and consider modulus of continuity. Well, if I and j are like these two numbers, so you don't flip the trajectory, then this difference is the same as for initial simple symmetric random walk. It equals s psi minus sj. Well, if you flip this trajectory, and again I and j are here, then okay, you have absolute value of s psi minus sj. And there is a possibility that, for example, I is here on one path, and j is here. Okay, sorry. Let me write like absolute value of psi minus absolute value of j, and with this, and this is less than or equal to s psi of I minus s psi of j. And now assume that one point was here at one excursion, and another was in another excursion. Well, if you flip both excursions, and if you do not flip both excursions, then the answer is the same. Okay, so in most cases, you see this is less than or equal to this. And what happens if you flip this one and you don't flip this one? So these are two different, so there are two different excursions. This means that you arrived to 0 here and you started from 0 somewhere here. So difference between this and this is equal to sum this distance plus this distance. And okay, this distance is equal to value at this point minus value at this point. And this distance is equal to absolute value of the random walk at this point minus at this point. So in all cases, this maximum does not exceed 2 times maximum over all I and j in this interval k and L s psi I minus s psi j. And we know that the Donsker scaling limit of s psi is a Brownian motion. So this sequence is weakly relatively compact, and you then by Prokhorov's theorem you have okay, and then you have nice estimates for modulus of continuity of this, and hence you have similar estimates of modulus of continuity of x. So actually this sequence is really weakly relatively compact. Well, if you know a theory of weak convergence, because I explained only a little bit of this theory in my course. Okay, now let's continue. Now my aim is to write stochastic equation for skew Brownian motion. So there are a lot of possibilities how we can do it. And the one possibility is this. Again, consider simple symmetric random walk. And now I would like to associate, so this is xn, and now I would like to associate with this xn certain simple symmetric random walk, and I will do it in the following way. So at first, I will color in red the steps when you exit from zero. And I will say that these black steps are normal steps, and these red steps are compensating steps, compensating or critical steps, compensating steps. Well, it follows from the Markov property that these normal steps, this is first normal step, second, third, fourth, fifth, sixth, seventh, and so on. They are the size of every, normal steps are independent, identically distributed random variables that are equal to 1 and -1 with probability 1/2. And these compensating steps, again, are independent, identically distributed random variables. They take values 1 and -1 with probabilities P and Q. And it follows from Markov property, okay, not from Markov, from the strong Markov property, that these red steps and these black steps are independent. And okay, we take some number, a number n, we consider xn, and what is xn? Xn is equal to sum of normal steps plus sum of critical steps. So let me denote T normal and sum k from 0 to n minus 1 indicator that xk is not 0 and T, say, critical or compensating. Okay, compensating, let me write compensating of n is the number of steps from 0. And this distance, so the value of the first jump in the normal mode, I will call xi1, the second xi2, third xi3, fourth xi4, so xi4 is 1. Now xi5, xi6, and so on, and the first red jump, the value of the first red jump, eta 1, then eta 2, eta 3, eta 4, and so on and so forth. And introduce random walks Sn and S eta. S eta is eta 1 plus eta 2 plus eta n, and S psi n is, okay, x of 0 plus psi 1 plus psi n. Then it can be seen that x of n is S psi of T normal n plus S eta of T critical, T compensating n, T compensating n. Okay, the next step. If we consider, let's consider the sequence absolute value xn. So then it's easy to see that absolute value of xn has transition probabilities plus minus 1 everywhere except of 0, and from 0 you jump to 1. So this is reflected. So this is simple symmetric random walk reflected at 0. Simple symmetric random walk reflected at 0. For simple symmetric random walk, we know a lot, and we have similar representation like steps outside of 0. Okay, T normal is steps out, number of steps outside of 0, and this T critical number of steps from 0. And for these, we know at first that the Donsker scaling limit of x and t over square root of n is reflected Brownian motion. Okay, let me write like reflected Brownian motion. Moreover, we discussed that the number of visits, so x and absolute value of x, have the same amount of visits. That amount of visits for, excuse me, modulus. Converges to t. Even more with probability 1 or and locally uniformly. What does it mean? This means that actually this divided by t converges to 0. Compensating n t. Because sum of this plus this is n, so this converges to 0. However, we knew more information about this. We knew that if we consider a pair, and again, the number of these compensating steps for absolute value of x and for x are equal. And if you divide this number by square root of n, then this pair converges in distribution to absolute value of a Brownian motion and its local time at 0. Where the local time of this process is the following. So local time is defined by the limit 1 over 2 epsilon, the time that this process spends in a strip minus epsilon, epsilon. So we calculate the time, and we divide by epsilon, and voila. So here is the limit. And okay, and now we know that x nt over square root of n converges to Skew Brownian motion. And on one hand, absolute value of this converges to some process, but on the other hand, modulus is a continuous function on this set of continuous or Cadillac path. So this converges to absolute value of the Skew Brownian motion. And next step, you see, you converges here, you convergence here. So actually, this process have the same distribution. And what about the local time? And the local time is calculated by this formula. You take the process and you calculate the amount of time that the process spends in minus epsilon epsilon. And we see that the local time of W skew at zero exists, and it equals the scaling limit of the number of steps that xn, the number of visits to zero. So the next step is to write that xnt over square root of n, the pair, t compensating of nt divided by square root of n converges to pair. The first one is this. And the second is the local time at zero of this, but the local time of zero at this is equal to the local time of zero at this, of this process. Local time of the Skew Brownian motion at zero. Okay, I cheated a little bit here because if every coordinate converges to a limit, this doesn't imply immediately that the pair converge to a pair. In this case, this is a true. This is a place that you have to think about. And now, we have this. And now recall representation. X and t over square root of n is equal to s psi of nt over square not nt, t normal of nt divided by square root of n plus I have to write here as eta of t compensating. Let me write it in the following manner. Sum k from 1 to t compensating of nt of eta k divided by square root of n. And now, let me apply let us discuss what is the limit of this. For example, what is the limit in distribution of this? Well, we know Donsker theorem that S psi of nt divided by square root of n converges to a Brownian motion. And let's represent this as S psi of n t normal of nt divided by n over square root of n, and write this as a composition of two processes. The first one is this, and we compose it with t normal of nt over square root of n. And we know that this sequence converges to t with probability 1, and this converges to Brownian motion in distribution. And we know that if one limit is non-random, then you have convergence of pairs. So over square root of n, t normal n dot over n converges in distribution to a Brownian motion. Okay, let me write like t, and t. And now apply Skorokhod representation theorem that states that there are copies defined on certain on the same probability space. So let me just write subindex n that are copies that convert to certain Brownian motion, and t in the topology so almost surely you have almost sure convergence in space of continuous functions. And if you have locally uniform convergence of pairs to pair, then you immediately have that composition of this and this converge to composition of this and this. And composition of this and this is, again, a Brownian motion. So on some probability space, composition of copies of this converge to a Brownian motion almost surely. Hence, you have convergence in distribution of composition of initial process to a Brownian motion. So this guy converges in distribution to a Brownian motion. And what about this term? What about this term? Well, I will give you rather idea how to guess a limit of this than a rigorous proof. But let us discuss. So what do we know? We know that t compensated of nt divided by square root of n converges to some process L of t, well, in distribution. Question. What about this sum where eta k are independent of this, and probability that eta k is 1 is p, probability that eta k is minus 1 is q is 1 minus p. Okay, again, assume that we applied Skorokhod representation theorem and that we have almost sure convergence to certain process. What can we say about, well, S eta of t compensated of nt over square root of n? Again, we consider this as composition S eta square root of n dot over square root of n and t compensated of nt divided by square root of n. This converges to L of t. And what is this? Sn, S eta. This is a sum of independent, identically distributed random variables. We know that, we discussed that the scaling limit of this, the almost sure scaling limit of this is equal to expectation of eta times t, or p minus q times t. And again, composition of this converges to p minus q times L of t. Well, this converges to a Brownian motion. This converges to p minus q times local time of this process. I have not discussed that pair converges to a pair, but the result is this. The limit of this satisfies a stochastic differential equation, satisfies equation with a local time. And equation has the following form. W skew of t, skew Brownian motion, is equal to a Brownian motion b of t plus p minus q times the local time of this process and 0. So we guessed, and we have like very strong, but maybe with some gaps, strong arguments, however, with some gaps, that confirm that the skew Brownian motion is solution to the following equation with a Brownian motion and with a local time. Well, we denote this p minus q by gamma, and it was proved by Harrison and Shep in 1981. That this stochastic differential equation has a unique solution for gamma less than or equal to 1. And okay, if p in 0, 1, then p minus q is between -1 and 1. And there is no solution to this equation for gamma such that absolute value of gamma is strictly greater than 1. Okay, so today we discuss the yes, please.
Sorry, excuse me. And why do we call it differential equation? Where
okay, stochastic equation with a local time.
Okay. Thank you. Maybe if I ask another, can I have another
Yes,
question?
sure.
Can we get back to the argumentation where we have conversions of composition to Brownian motion?
Yes.
Here, yes.
Uh-huh.
So, yes, we have two things. Some converge to its Donsker limit to
Yes.
Brownian motion.
Mm-hmm.
Some converge to that. Okay, I understand that their pair converge weakly. Okay, we can have that their copies converge almost surely.
Yes.
And you mentioned something about uniform convergence, and
Yes,
yes, we want
you
uniform
have
convergence.
convergence in the space of continuous functions. And
Ah,
topology here. So topology in Donskir's theorem is topology in the space of continuous functions. So if you consider T0 T, then just uniform convergence. If you consider space 0 infinity, then locally uniform convergence.
okay, thank you.
And
I thought it was weak convergence.
no. And if Fn converge to F locally uniformly, and Gn converge to G, and all functions are continuous locally uniformly, Gn acts from 0 infinity to 0 infinity, and Fn are defined on 0 infinity. So composition is well defined. Then you have locally uniform convergence of Fn Gn to F of G. And this is Fn, this is Gn.
Yes, and this is for copies, so for originals, it's weak convergence.
Yes, convergence in distribution.
Okay,
Yes.
thank you very much.
A few words about stochastic differential equation. So in some sense, you may write the differential of W skew of T is equal dW of T plus gamma dL0 local time of T. In some sense, the local time is so this is approximation. So the function 1 over 2 epsilon indicator x less than 2 epsilon in some sense converge to Dirac delta function concentrated at 0. So in some sense this term can be written as follows: gamma times delta function at 0 of the process W skew of T dt. So in some sense, this is generalized drift that corresponds to Dirac delta function concentrated at 0. And Mykola Ivanovich Pilipenko was the first who introduced such equations, and actually he was the first who wrote this integral representation for the Skew Brownian motion, and he gave rigorous meaning to this term, and probably it seems to me that his original paper was published in 1976 and then in 1978 in Proceedings of Soviet Japan Symposium on probability theorem. Well, he considered another approach than Harrison and Shep. Harrison and Shep, they use Tanaka formula. They make some transformation of this process. Then using Tanaka formula, after that transformation, this local time disappears, and they got usual stochastic differential equation. And then they got existence and uniqueness. And Portenko's approach was different. He studied semigroups. Then he deduced from concrete from the semigroup theory, from transition probabilities, that if you have a Markov process with with these transition probabilities, then there exists a Brownian motion and certain continuous additive functional, like local time of this process such that you have this representation. So in some sense, this can be considered as generalized stochastic differential equation. And now let's consider the following model. Consider random walk xn, Markov chain xn, with the following transition probabilities. So again, outside of zero, it's a simple symmetric random walk. And if you start from zero, then the probability that you jump into point J is equal to probability that certain random variable is equal to J. Well, and J is integer number. And assume that expectation of eta is finite. So outside of zero, simple symmetric random walk, you hit zero, and the next step, you exit by a jump. So if eta takes values plus and minus one, then we have previous construction, and again, then you jump maybe down, and so on and so forth. The question, what is the scaling limit of x and t over square root of n as n goes to infinity? And okay, let's start. First, consider absolute value x of n. It is a Markov chain with transition probabilities. 1/2 everywhere if you start above zero, if you are not at zero, and you jump only up, and the jumps have distribution absolute value of eta. So p I plus minus 1 are 1/2 if I is not zero, and p0j is equal to probability that absolute value of eta is j for j non-negative integers. And the picture is this. So you walk, and then you jump up, then again symmetric random walk, and they jump up, and so on and so forth. We discussed this model, and we discussed that the limit of x and t of this reflected random walk is reflected Brownian motion. So let me, yes, reflected Brownian motion. If expectation of eta is finite. If expectation of eta is finite. And now let's consider this random walk as the sum of steps in normal mode and steps and jump from 0. So we say compensating. So similarly, x n of t over square root of n is equal to, okay, absolute value of xn is equal to s psi, so this t normal, n plus s eta t compensating n, and we know that Donsker scaling is a reflected Brownian motion. Actually, we proved the following way. Again, this t-normal n divided by n converges to, so this number is close to n, and then we prove that S psi converges to a Brownian motion W of t. And we discussed that this pair converge to non-negative process, and hence this second term converge to something. So if some converges, the first term converges, so second must be converge. So the scaling, okay, the scaling. And
I'm
t,
sorry.
yes.
Maybe we should write s not at
Yes,
modulo.
absolute value of it.
Thank you.
Absolutely correct. Over square root of n. So this converge to certain process, which is non-decreasing, because absolute value of etas were non-decreasing. Well, we pass to another probability space. Again, we used Skorokhod representation, and that this reflected process probably it is not good. Okay, let me write here W reflected. That W reflected of t is equal to W of t plus L of t. And this process is non-negative. This is a Brownian motion. This is something, this process is continuous. This process is non-decreasing. L of 0 is 0, and it can be seen that L does not increase if this process is strictly positive. So L may increase only when this reflection hits 0. So we may identify the limits of this with solution to Skorokhod reflecting problem, and we have a formula that L of t is equal to minus minimum of W of S, minimum 0, Ks in 0t. And if we return back, so, and now, again, we have a recall that we have a formula L in terms of V, but we have a formula L in terms of the local time of this reflected Brownian motion. It's equal to limit as epsilon goes to 0, 1 over 2 epsilon, integral from 0 to t, indicator that W reflected S less than epsilon ds, and I denote this by L reflected at 0, local time of this process at 0. And now we return back to original random walk. And again, we have so the position of original random walk is a sum plus minus 1, so with probability 1/2. So you take terms, you calculate number of, you calculate the sum of jumps in normal mode, calculate sum of jumps in critical mode, and you have similar representation as xi t normal n plus s eta t compensating n. Now, one small remark. The number of jumps in normal mode for x and for absolute value of x is the same. The number of jumps in compensating mode, again, is the same. You use etas and you use absolute value of the same etas here. However, I wrote here tilde. So actually, xi1, xi2, xi3 for this process and for this process are different. Indeed, if you jump below 0 and take absolute value, when you have a jump here up, then you should have the jump here down. And when you jump down here, you have to jump up here. But nevertheless, these xi tildes are independent, identically distributed random variables. And we know that t and t divided by n converges to n. So this converges in distribution to a Brownian motion. Well, to some Brownian motion, b of t, another Brownian motion. Not this one. Not this one. And what is the limit of this? What is the limit of this? I know that this sum t compensated of eta k and t absolute value divided by n converges to a local time of that reflected Brownian motion at 0. And the equation is, and if I do not write absolute value of etas, but just etas, a small exercise is to prove that this sequence without absolute values converge to expectation of eta to, okay, so if you delete this, expectation of eta divided by expectation of absolute value of eta as n tends to infinity. Okay, again, this is an exercise. And well, I do not discuss that the pair this and this converge to certain limit. This is true. Let me only write the result. What is the Donsky scaling limit? And the Donsky scaling limit of x and t, so over square root of n over square root of n over square root of n satisfies the following equation. Okay, y of t is the limit of this is equal to Brownian motion. Okay, I may not write tilde plus expectation of eta over expectation of absolute value of eta times local time at 0 of this process. And you see, this if you consider absolute values, then term with absolute value of eta converge to local time of this process, of the process like reflected Brownian motion. And the local time for the process and for absolute value of the process coincide. So, well, theoretically, I have to write the local time of the limit of this, but the local time of limit of this is equal to local time not of absolute value of y, but of y, because the formula is the same. And well, we see that the limit satisfies the same equation as equation from the paper by Harrison and Shep. And that's true that the limit is skew Brownian motion with parameter gamma that is equal to absolute value of eta divided by expectation of absolute value of eta, and this parameter is between -1 and 1, and this parameter is actually natural. Okay, that's all for today. Thank you for your attention.